continue to the next subchapter talking about how this means in high order derivative and try to find the maxima. So that is actually the concept is coming from and getting the more deeper from the 7.4. So let's see from the mind map. I give you these two sentences which in the book and ensure is you can find the relationship. So when we link learn from last video to introduce the derivative and try to find the derivative of the function, we just gave this derivative class or the this function with two arguments. First argument is f. So let's see. So what our syntax is derivative. Ensure is capital D, and we gave a function, then we gave the x. So then we get the derivative result. And bear in mind is when we do this way, is by default is create the first order derivative. So, but in the calculus we learn is we can have a second order derivative, third order, and more the higher orders. So if we see here is the order, we put that as the it's equal to n that we want to introduce is n is plus maybe so we see here is equal to 2 or more. So what we can do is simply we still use this SimPy derivative function, but now we give f and give x and give this n. So then that is the syntax. So let's ensure is this should be our not our it's a pseudocode, but just ensure to give you is derivative or idea. They can it can accept 3 arguments. When you send our third arguments with 2, or even you can send with 1, so you get our higher order derivative calculation. So let's make some these demos. We will try to find this derivative way, and the result is try to find the maxima using this new learned high order derivative. But first is let's see. So if we go to just roughly the simple one, the from SimPy import symbol and the derivative. I think it's that's enough. So let's make this one. It's too high. Let's use our simpler one. So this one is good enough to introduce the second level or the second order. So let's put us f is equal to 2 times x. So just the 2 orders is just easy. So we we should first is make symbol definition, and now we can do this. Now f is our the function. Then what we will do is we put is d1 is equal to derivative f x. So when we do this, we see d1 is this one and d1 dot. So before we enter, that should be here. This 2 times 2, so 4x plus 3, and this 1 get to 0. So 4x times 3. So if we do this d1 another, so if we see is now I want to do this derivative f x, I give a 1. So you can see is no error. So what is d1 1 means is exact the same, and also if you do this dot, you get the same result 4x plus 3. So that means is by default is treat you is the third argument is 1. So with this expanding the definition, so let's make this d2. So go to the second order, so derivative fx2. Then d2 you can see here. They have another this tuple to indicate is now x with the second order of the derivative. Now, if you make that is the second order, that is like as you do the another the first order derivative for this first order derivative result. So then we can imagine that will be the just the number 4. So let's see. So dot. So you get 4. So that is the way is no any the specific, but to use this higher order derivative, you just add in the third arguments. But what's the usage for this high order derivative? We will use this way. So show you how to use the first order and second order to the function. And they help us to find the maxima and the minima of an interval. So with a range of the order or scope that find this maxima, minima. The purpose why is we use the higher order derivative is the derivative actually is measured those the rate of change. So is you have the first order to measure the rate of change of f compared to the x, and the second order is this rate of change of this first order's result of a derivative. So that like in the physics is the first order is like for applied to the derivative applied to the distance or length will be the velocity, and the second order is the accelerate. In physics, it may not be easy to think about the third order, fourth order, but in mathematics, it give you freedom to make those math thinking. So the third order is very easy to measure the rate of change for the second order derivative result. So and then this through that method is even you see this in the zero order, the function is like a very complex curve. But in the first order derivative, we will see the rate of this value change. And when we add more orders of the derivative, you must learn from the calculus classes. It getting the different those functions get one function is one order is make this to our the line linear. So then you can get this maxima, minima, so easier. So if you only look at this to tell me A, B, C, D, which is the maxima, which is the minima, is not easy. So that is the idea. So instead of we just use the command is let's create a program and follow this one by one to find this the numbers of those maxima, minima. So let's do this. So it's 0, 5, 0, 7, 0, 5 is the find higher order. Find maxima, minima dot py. So actually here we only have one, so we don't need this one. And once we have this, I think I can update this one. So you see in here. So I have the code name, so that you know when I create this one is linking to here. And same is after this video is I may have more to put in here. So and you can see where I'm using icon, use a MISC icon and put this launch. So that is our code, so that you get another indicator is this to be program is related to this 7.5. So the purpose using higher order derivative to find maxima and minima. Now it's already moved to March. Time flies. Hope you enjoy the learning. So consider now we have this function. So we got this function and we can do this calculate. So let's see. So we have definitely it's from SymPy as import is this S is not in capital, but the symbol in capital. Remember, symbols is in the small case, and we need the derivative. So maybe we should have this pp print. Then, if then what we will have is we put our x is the symbol, and we put this f is, yeah, later we can easily convert this to accept the user input our function. But let's just do this simpler. So plus 550 times x. So that is x times 5. I think I don't have the issue, right? So yeah, I can use a pretty print. So let's make sure we have our result. So here x this is a higher order this function. Notice I have used the squares. These define the domain to close. So this domain later on you can see is we just gave this definition. X min is -5, x max is +5. So we will ensure it, and we need to have a solve later on. So let's give a solve also a load. And let's say, so I want to find this maxima and minima, but actually this curve is changing the direction several times. So this one is we call this around this area is maximum. It looks it's quite big. And this C is also, if you just see from the range 0 to 2, is also the maximum of this range of curves. So actually they call those as the local maximum. So A and C are local maximum, and B and D are local minimum. But what we want to find is actually A definitely is higher than C. B is if on this the absolute value is lower than D. So A will be called as the global maxima if we see from -5 to +5. So and D will be the global minimum. So what we want to see is we need to distinguish this local, global, and we find this maximum, or we call that is the maxima within given range, -5 to +5. If you put this longer, this may be the we don't know this will changing for what, but it will give our the different range. So let's try to see import the matplotlib.py plot splt. So let's see whether we can draw this PLT show. So and let's create some range. So I in range. So x-axis is y. Oh, let's see. So x point, y point is also empty. Let's make our plotting to see. So, so the solving. So what we will do is y is also this one. So if I want to make this one, so it's f. There's so print. Oh, so list is now I put this f is and I put this x. Let me see. So if I put this here, Python. So I load this and give x, give f, and then f there's dot solve. It's add oh, which is the difference. Oh, so maybe yeah, I need to remember the syntax. So I have the solve. Okay, so solve f, and then is I put solve f. I got those error. Those are the solve is the yeah. Let's see. So if I put f as the with subs x minus 4. Okay, so that is the way. So I should use this one. So when I want to get y, so for x in range, let's see. So maybe it's 400, 100. Maybe so we got this 101 and this x points dot append x. It's a very easy. Then this y points append is the f dot subs x is the let's use this I sub by I. Then we got this to list. Then is we just plot this x point, y point. So quit here. Let's make a run. So we got this the drawing. So that is from minus this to here, and let's make our zoom. So here, let me zoom. It's almost like our this minus. If I keep zooming here, I think it's because I have not so this only is the this is in the interval is 1, so it's not continuously. But you can see here is they got certain this kind of the curve a little bit, but once we have that in more detail continuously, you may find this one. So that's the difference. Is let me put this just our sample. Show in this create line curve plotting. So let's make that here. Then what we will do, let's see here. So I can do another way. So I put this to divide it by 10. Out from here is divided by 10. So let's have a look. It's also here looks like it's a little change. So 20. So from 100 divided to 20, then we got this negative positive 5. Oh, now it's we can finally see this curve. So I just use a tricky way to make this range with the interval, and then make that lower than the 5. Make that into this negative positive 5. So that is also, if you want this bigger, so you can see is I now this will give more points. So let's see here. So I got another. So that from here I can easily do this. Not like this. Let me zoom. So zoom on here. So you can see this curve is getting the short. So that is our, just I want to give you some visualization of this one. Then let's see, so what we will do is we learned on the high order derivative. So we have this f, and what we will do is we define the d1 is this derivative, the first order. Then we will use this critical point to solve the d1. So let's say d1 is the derivative fx. Remember here we missed this third argument, but by default it gave our 1 and dot. And then this we put this critical. So let's critical points equal to solve d1, and we can print d1 and print critical point. Oh, so we gave f. So let's see here. So we have our function here, and this is the first order. So first order is this 5 go to the coefficient, and it's a lower 1, and this 3 times 30 is 90, and this number 2, and x is go to the 0 order. So that is the first order derivative. And what this critical points means is a critical point is give you 4 points. This critical means they give show here is corresponding to these 4 points as the maximum or maximum minimum in the certain range. So those are the 4 local maximum minimum. So we will use we can see here is this A is the third one is the most lower, and B is the most higher. C is the one is this one. C is this one. A, B, C. So A is maximum. The D is the lower. So we define this A, B, C, D. Then this we have this D2. So now let's see D2 is the derivative fx2 and make that dots and print. Let's use this D2, and here just use the pretty print. So let's see our result. So that is makes nicer. So this is the first order, this is the second order, and this is the solve. Thus, you can see here the number 2 and number 3 are positive, and these 2 are negative. So this 9 minus this square root 71 will be this point C. So C is this one, and B is 0, and C, this one is the most lower. I think is A, and this is D. So we define like what the authors do. This A is the critical points 2. B is the critical points 0. Oh. C is critical points 1. D is critical points 3. Then we have these just 4 the symbols. We already have D2 here. Then let's use this the evaluate. So this evaluating if the result is less than 0, point is local. So and if the result is greater than 0, is a local minimum. The less than 0 local maximum, and the result is 0, then test is inconclusive, and we cannot deduce anything about whether critical is local maximum, local minimum, or neither. So we're evaluating the second derivative test at the critical point. Tell us that point A is and point C. So A and C are the local maximum, and the B and D are local minima. So let's print those. So print. Just use this print is D2 is the evaluate point B is the let's see the 0 with dot to 5f. Then we have a format with d2 subs xb evaluate function. So let's have a look. So we got the evaluate point B is this one. So using the same way, so let's do the another 3. So we will have the CAD. So we replace this CAD. So let's also print our evaluation on second order DV. Okay, so then we have our here. So this one, so you can see this 4 evaluation result. And then what we will do is we will use this X range. So we also will evaluate the X this boundary value. So when we see the let's see, so here the boundary evaluate on the boundary value, and what we will do is let's copy to and apply over here. So when we do this x, so we don't give this b, so the x minimum, and here is the x. Oh. I running press F11, so there is go to the full screen. So x minimum, x maximum. So that's the same using the evaluate function. So now we have another the number. So its x minimum should not be the 1600. So it's -5, +5. So let's see. So I transfer this d2 sub x. So this should be the f. So not in this second order. So okay, so 375 minus 375. So by this calculation, we examine the function value at all the critical point. You should have those maximum local, the maximum, local minimum. Those are the critical point that you can use these critical points, this function to solve. When you solve that, you got those critical points. And then the boundary value is also the critical point. So you got 4. So when we adding that into this solving result, and then this we can compare to them is we see the this A, the point D is the global maximum, and the point A is the global minimum. So that is the way. So we can also evaluate this B and D, compare with A and C on the function level. So those are the way is you can see is when you do this higher level derivative, it can help you to find out those critical points, because you will do the solve on the on the derivative level, or the higher derivative level. That if you try to do the solve on the f, you can only get. So if I do this solve in f, I only get 2 these values, but in the higher order derivative, I got more the value result, which we can call that is the additional those the critical points. So this is, I hope I put that into our program. You can try to run yourself. You can also run this and to see. So this is y is the f, and if I put is let me see. So we have the d, right? So d is y1. So let me also to see is what we can do. So y1 points is also this, and the second order, whether we can do them as well. So we have D1, D2. So let me see here. Let me copy that to draw the 3 lines. So Y1, Y2, and here I use D1 and D2 to see. Then here I just keep using this way. So now is I use the y1, this I use y2. Yeah, here is underscore y2 points. So it's this one. So let's see what we can get. So y2 point is not defined. So y2 point is here, and this is the y2 points. This is the y2 points. Oh, so what that means not defined. So I think it's not fully saved. Oh, line 1 in module. So it's defined, I think. Okay. Yeah, that is great. So I don't have that the legend, but it's fine. So, but you can see these should be our the original, and one is the first order, another is the third the second order. So you can put those different derivative result into one plot. It just gave a sample the thing. So you definitely, I believe, from your learning until now is you can make this the diagram in more beautiful way. So I just leave that on this ugly the interim result. So let you to optimize that. Okay, then thank you. I think is with this subchapter is we learned is how to deal with the higher order derivative, and the next chapter we will find this global maximum, not using our these subchapters way, but we will using another method is called the gradient ascent. So see you in that video. Bye for now.